Hello, everyone. The following is the second in a series of lectures covering Chapter 41. Today, we'll be talking about a particle inside the box. We already talked about how the wave function for a free particle is pretty much a sinusoidal function that has the same amplitude everywhere. But in the real world, there's there's constraints to where a particle can go, whether it's an electron orbiting around an atom or even atoms themselves. So a wave function generally has to obey some kind of constraint. And we'll kind of take a look at that by first considering a very simple model that will maybe not the most realistic model for what a particle is going to be doing. It is sort of a basic one that which can then be extrapolated to more realistic cases such as electrons around atoms and such. This model consists of a particle all by itself in an empty box bouncing around the walls. The particle has some speed, it has a mass, and while we're at it, we're gonna keep things to one dimension. So there's one wall position at the origin, x is 0, and on the other side at a position of L, so the distance between the walls is L. So the second wall is at the x equals L, and so the particle is confined to this space. In classical mechanics, we look at this particle and you'd be able to, know where it is at any point in time. If you know the speed, energy will be conserved. So there's, just particle bouncing around with the same speed at all times, maybe a different velocity depending on its direction, but still. The particle can have basically any energy. Doesn't really matter. In quantum mechanics, though, due to its wave nature and its corresponding wave function, we'll see that only certain energies are allowed. So let's look at a quantum mechanics perspective of what a particle in a box is. So the particle in this box has a wave function, and the consideration is that for the purposes of this wave function, the wave representation of the particle only exists inside the box. That means that there's some amplitude to the wave function inside the box because the particle is only can be found in there, but outside the two walls, outside the two edges of the box, you cannot find the particle. So the wave function would just be 0. There's no you can't find it, so no amplitude. The idea of the walls of the box from a quantum mechanics perspective, from the perspective with a wave function, is that the ends of the box are essentially potential barriers. They're this, impassable walls of infinite potential energy. So the particle will never have enough energy to overcome these barriers and go outside the box. In classical mechanics, we could just talk about the particle, physically moving around space, and it'll never, just going up and down. And there's physical walls. But from the perspective of quantum mechanics, we have to describe the walls as literally being potential barriers, right? This area where the energy threshold to be surpassed is, infinite, so you're stuck inside space. So your wave function basically is describing the particle, but this wave function is pretty generic in the sense that it's just kind of giving you a sinusoidal wave. So we haven't really accounted for the fact that the wave, the particle, is constrained between the two walls. And if we do that, then we'll get a more accurate, more specific wave function that actually represents a particle in the box. So we need to apply boundary conditions, which is the fact that outside the walls, the amplitude drops to zero. We can't find it outside. So that means that at the edge cases, at the corners, at 0 and L, the wave function is 0. That's kind of how, when you saw like a standing wave, you had to have nodes at either end. So for this to be true, if at x is equal to L, the wave function is 0, then because there's a sine function here, that means that whatever's inside the sine function must make sine equal 0 at x is equal to L. So for sine to be 0, the input has to be any multiple of pi, and because of that, it leads to the wavelength of the wave function having to be some number equal to 2 times the length of the box divided by an integer. In other words, there's only certain allowed values that the wavelength of the wave representation can have to actually exist in this box. So when a particle's inside the box, its wavelength can only take on certain values, kind of how like a standing wave can only have certain harmonic frequencies or wavelengths. So if the wavelength is basically quantized, can only have some values for the particle in the box, then the wave function represents it as well. So the wave function now becomes, rather than having lambda, you have the sort of requirement that lambda must equal to L over n. N is just some integer, n 1, 2, 3, and 4, or so on. So now the wave function basically specifies, the quantized wavelength. A, again, is this normalization constant. So it's just there to ensure that if you were to integrate the wave function over all space, you get a probability of 100%. So for this situation, you can actually do the integral and find out that A must be like the square root of 2 divided by L. And the full form of the wave function for the particle in the box is the one shown below. So the wave function is known, and again, only a few wave functions are allowed, those that follow this sort of quantized wavelength. And the wavelength of these functions actually resemble the harmonic wavelengths of a standing wave on a string. And you can also take a look at the probability densities, the square of each allowed wave function, and you'll note that their values are always positive, since they're representing a probability density. Probabilities, can't be negative. Again, I'm gonna remind you that these wave functions, this is not physically showing you like a wave that's there. This is not like a wave. This is not a string here you can like touch or you can watch moving up and down like a real physical standing wave. This is showing you the wave function. This is just some physical representation, a non-physical uh, figure here, a non-physical shape. Same with the probability density. This is just showing you where you're gonna be more likely to find the particle, but it's not like an actual physical description of the particle's position, just probability. So kind of here in the slide, kind of restating what I just said, where only certain wavelengths are allowed for the particle in the box, just like how certain wavelengths are allowed for standing waves. And again, the wave function is just describing a state of the particle, nothing else. Now, because the wavelengths are quantized for the particle in the box, and the wavelength is related to the particle's momentum, it must mean that the momentum is also quantized. So you can use the de Broglie wavelength to find what the quantized momentum is. And so there's different momentum levels for a particle. Inside the box, we're basically saying that there's no potential energy. It's zero. So the energy of the particle in the box would just be its kinetic energy. Its kinetic energy is related to its momenta, So then the total energy is also quantized because momentum is quantized. Therefore, the energy of the particle can only take on certain values. And the lowest possible value would be for n is equal to 1. So that's a wave right here with a wave function where the wave, where its wavelength is actually twice the length of the box. And the lowest possible energy is called the ground state. That's when you have the term n equal to 1. So the lowest possible energy a particle in a box can have is shown here. So it depends on the length of the box and its mass. H is just Planck's constant. So any energy level above that, you can find the energy for that level if you just take the square of the level times ground state energy. So the second level has 4 times ground state energy, the third level has 9 times, the fourth level has 16, and so on. These are called the excited states, since you have to absorb some energy to jump up to these states. And again, this is the whole idea of quantum physics, where energy of a particle is not a continuous value that it can have. It can't be like a car that can accelerate to any velocity and any energy. It can only jump to different energy levels. So here you see kind of like the energy distribution of the particle. So the particle in the box can only have energies in this rungs on the ladder, can't have anything in between. And also note that the quantization of energy implies that the ground state is not zero. It's some function of the mass and the length of the box, but still not zero. So by default, a particle always has energy. There's no such thing as a particle with zero energy. Also, that means that because this energy, in the case of the box, there being no potential energy means that the energy must be kinetic energy. That means that there's non-zero kinetic energy even in the ground state, which means that the particle can never be at rest. A particle is always moving, according to quantum mechanics at least. So in this quick quiz, we consider 3 particles in the ground state stuck in a box, and we want to see which one has the highest ground state energy. If you look at the ground state energy here, the only thing that sets the particles apart, because they're in the same box, so the length of the box is the same, the only thing that sets them apart is their mass. So energy is inversely proportional to mass. Whichever one is lightest will have the most energy. An alpha particle, being a helium nucleus, is the heaviest. Second heaviest is the proton, and then the lightest is the electron. So the electron would have the highest ground state energy. Now, this second part is asking which one has the longest wavelength. And if you'll recall our discussion for the particles in the box, the wavelength, kind of like harmonic wavelengths, actually have to be some integer division of the total length of the box. So whatever wavelengths are allowed just depends on the length of the box. Doesn't actually depend on the mass of the particle. So they all will have the same wavelength. Okay, so what happens to the energy levels if you double the length of the box? So the if you look at the formula for energy, it's inversely proportional to the square of the length of the box, and so every energy level would decrease if you increase the length of the box. So the values of energies will be a lot smaller to be closer together. Okay, so the question here is just asking you to find the energy levels for electrons in the first 3 ground states. So once you get the first 3 states, so the ground state and the first 2 energetic states. So once you get the ground state formula figured out, you can get the 2 first excited states by multiplying by n squared, and that will be all. So this is something we'll probably expect you to do. So if you want to find the speed of the electron, well, just know that again, all its energy is kinetic energy inside the box. So you can relate the energy to the classical kinetic energy formula. This still works. This is still a totally valid formula, and does calculate the speed based on the energy and mass of the electron. So it's moving pretty fast, not relativistically fast. So we won't have to worry about relativity in quantum mechanics for this course. They won't be combined. And while you're at it, you can actually find what the ground state energy is for a baseball, as well as its minimum speed. And basically, with the idea that anything must always be, that any particle, any system can't be at rest. It always has a minimum energy, a minimum kinetic energy. Then it turns out that a baseball nun in its ground state must have an energy of, sorry, must have a tiny energy and have an incredibly small speed. So yeah, technically nothing in the world then is at rest, because particles are not at rest and everything's made of particles. But the rest speed, the rest energy is so small that from our own real world perspective, it's zero. And now we're gonna look at the baseball that's moving really fast. Maybe a good batter hit it really hard, and you can then find, based on its ground energy, you can then find what quantum state must be in to achieve the speed. And here you see the problem in trying to treat real world objects as quantum particles, because if we treat the baseball as a quantum particle, then to get the speed it has, it must be on a quantum level of 2.26 and 10 to the 37. So its energy is this squared times the ground state energy. And so this is like a huge, incredibly huge number of quantum states of like a really high quantum level, because the difference between energy states. So even if the baseball is made up of particles with quantized energy, so technically yes, the baseball only really has quantized energy states. The difference in energy between each state, so from one state to the next, it's just a tiny, 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 tiny jump in energy. So altogether, um, energies, seem continuous in the real world, because the distinction between their possible states is so small that the transitions just seem like continuous. You're not going to notice the baseball, changing states, because the change in states is so small. So this is why we don't really talk about this when we talk about real world objects. Okay, so don't worry too much about the calculus here, but what they're basically doing is there's just finite expectation value for the particle in the box, and the result for that is L/2. So this is halfway right in the middle of the box, which makes sense, right? Because more often than not, the most likely place you'll find something is in the middle. And if you look at the wave functions for the first three energy states, you'll see that effectively, if you take the average is always going to fall in the middle. Even if, say, for the second energy state, the amplitude at this point is a node. So in this area, the probability of finding a particle here is actually really small, because the amplitude is like near zero. The areas here and here have high amplitudes, so there's a high chance of finding a particle here or here. But so that averages out actually to the middle being the average place to find the particle. To kind of give an analogy in the textbook written here, where you know in the grade distribution for a final exam could end up with a average score of 50%. So where the grade distribution looks like this, where the it peaks right on the average, or it looks like this, where there's kind of like two curves going on. Both these curves would still have the same average. So just to kind of relate that to standing waves again, the whole thing of boundary conditions for the particle in the box, is similar to the standing waves on a string, where there had to be nodes, point of node displacement, no amplitude on the walls. So same thing with the wave functions in quantum mechanics. And in the same way that this boundary condition led to standing waves having, this harmonic wavelengths and frequencies, so was the case for the quantum wave functions, where you only had, quantized wavelengths that are possible, leading to quantized energy and momenta. But of course, they're not the same, because wave functions in quantum mechanics describe a state, while wave functions in classical wave mechanics describe, the physical position and shape and, kinematic properties of a wave. That's why in quantum mechanics, waves can have, complex elements to them. And also in classical mechanics, the energy of a wave was actually related to its amplitude, not its frequency. While in quantum mechanics, the frequency of a wave is actually related to the energy of the wave particle system. And there's there's no sort of like nodes in quantum mechanics wave functions. Like there's no physical node. There's no point where like something's tied to the wall, in the same way that it is for a, real mechanical wave. And this statement just kind of summarizing that not just for a particle in a box, but whenever, a particle is subject to some kind of boundary, some kind of like, whether it's in an atom or between a potential well or like some kind of crystal lattice, some structure, the fact that there's some restriction put on the particle, leads to, its wave function, its presentation. It only can have certain values that, meet the boundary conditions. So that leads to the energy always being quantized. So in the real world, everything, has some restraint and limits and put on it. There's no free particle, and as such, that means that everything observable has quantized energy and quantized wavelengths and so on. So below there's kind of like a list of examples of, typical sort of boundary conditions for particles and atoms. Anyways, that's all for now, and I hope you join me next time. Thank you.